Hey everyone, how's it going? Today we're going to talk about the water cycle. Last time we talked about the carbon cycle, and in a lot of ways, there's a lot of similarities here in terms of all of the water on Earth that exists today has always existed since Earth was formed. Okay, so we don't lose water molecules. Um, they're just transferred to different areas in different forms at different times. And so let's get into it. Okay. Um, we know water is a necessity for life. You probably heard somebody say that at some point. Water basically is life. In fact, if you look at the human body is something like 50 to 60% water. And if we even just took a look at one of your cells, we'd find that the cell itself is over 70% water. So it's needless to say that we need fresh water to survive. However, if you look at the water on Earth, 97.5% of all of the water on Earth is salt water, which is an undrinkable form, like an unusable form for a living thing. The remaining 2.5% of all water on Earth, over 99% of that is in either glaciers or permanent snow cover or in groundwater. In other words, inaccessible to most living things. So all told, less than 1%, or really 0.3% of fresh water is found in lakes or rivers, which are like the available surface forms. So since if you think about it, all living things depend on this like really small supply of surface fresh water. Um, think about the impacts that a lack of water can have on an ecosystem or really just an individual. You can go weeks without eating, but only a very small amount of time without getting water. Um, so as humans, of course, we've come up with technologies that will increase water availability. Like we can dig wells to get at groundwater. We can collect rainwater. We can use desalination techniques. Desalination techniques is just salt removal. And we treat our wastewater at water treatment facilities to get them back to a usable drinking form. But we know still that clean, safe drinking water, it's really not always available in many parts of the world. Okay, so it's just interesting to think about some of the privileges that you have in terms of living in a really well-developed and first world country where, drinking water is for the most part readily available. But in other places, it's not readily available. So um, let's take a look at this picture here, and really encompassed within this picture is the entirety of the water cycle. Um, we're going to get into it in really very basic terms, but again, just like the carbon cycle, the parts of this cycle could be discussed at great length, right? The science behind many parts of this cycle are still being studied today, and we could go into each of these terms at a depth that is really just beyond the scope of this class. So for the scope of this class, we're just going to go really, really basic. Um, let's start with evaporation. So I'm looking over here at evaporation. Um, so we could start with the surface of the ocean here, or even this river over here, or this lake right here. And at any given moment, there's going to be water evaporating off of that surface. Evaporation happens when water molecules that are in the liquid state right now will get enough energy to pass directly to the gaseous state, okay? So water can be found in a few different states, the liquid, the gas, or the solid state. You kind of are familiar with all of those states at some point. Um, the energy that it takes for water to pass from a liquid state into a gaseous state in this instance is going to be supplied from the sun. Okay, so the radiation that comes down heats up the surface water and allows the water to pass from a liquid state to a gaseous state, and we call that evaporation. Water in a gaseous state we call water vapor, and as the water vapor heats up, it's going to rise into the atmosphere. Um, and as it rises, the overall temperature cools. And when the overall temperature cools, the water vapor condenses. This is condensation. Condenses into little droplets that sort of form around air particles or dust in the sky, in the atmosphere, and that's quite literally what forms clouds. Is so this like water vapor that forms around dust particles in the sky forms these really big white puffy clouds that we're familiar with. Um, Once you have clouds that form, you see this thing called transportation, and that word means exactly what you think that it means. It's that once water vapor is trapped in these clouds, clouds can move from one area to the next, and so water molecules that were originally found in this area could move all the way over to this area, and so that's just transportation. Um, we know that as clouds pick up more and more water vapor, the water droplets get heavier and heavier. And when those droplets get heavy enough, they will precipitate down. So precipitation here. Now, generally, when we think or talk about precipitation, we're talking about rain. But we could also be talking about snow or sleet or hail. But let's talk about rain first. Um, they could this water vapor could, or these water molecules could precipitate back down into the same area in which they started. Um, so the rain could go right back into the ocean here, and you might just get a little small bit of the cycle happening right here, where the water vapor precipitates down, evaporates back up, condenses, precipitates, and you get this cycle going here. Or maybe the precipitation occurs over this mountain. Okay, and since the air is going to be cold enough, that precipitation might be snow. Okay, it might be snow here. And if things never warm up in that area, that water will sort of be stuck there in the snow form. Um, if that water molecule came from the ocean, the cloud was transported over to the mountain, and precipitation occurred here, the water molecules will be stuck in this snow form. However, if things do warm up, and well, we know that they are, there would be what we call snow melt runoff. And snow melt runoff, I don't know if you believe this or not, but it actually causes rivers. So snow melt runoff is one of the big causes of rivers. Now let's talk what happens when water that becomes runoff or precipitates onto the ground. What happens to that? So most of it is going to do what we call percolate. If you've ever made coffee, you know what happens as water percolates through the beans, but it percolates down into the ground. And for as much water as you think that you might see in like rivers or lakes, much, much more of the Earth's water is actually percolated down into the soil and is located underground. And we see these over here in this groundwater. Now, in terms of seeing rivers or lakes only happen once the groundwater is completely saturated. So if you were to go outside and pour some water into the grass, it's not going to sit there on the surface, right? It's going to percolate down into the grass, into the soil. However, if you just turn your hose on for 30 minutes, eventually it's going to stop percolating down into the soil, and you'll have surface water sitting there. So anywhere that you see a lake or a river is where the groundwater has already been completely filled up, and it can no longer percolate down into. A pretty good example of that, whereas if you ever live somewhere where during rainstorms, like a little creek might occur, but when it's not raining or it's been dry for a while, it's dry. That's where you know that the groundwater is swelling and it's pretty full. So that's just something to look at maybe when you're outside one day. And so that in general is the water cycle. You have evaporation that condenses into clouds. It can be transported somewhere, and eventually it precipitates, and it just keeps going round and round and round. Of course, there's other factors at play here. You might see this term, and that term is transpiration. And so let's talk about what transpiration is. That's basically evaporation of the water that plant roots take in from the soil, and they take in water to do things like move nutrients throughout the plant body, to produce the things that they need from photosynthesis. But what happens is the plant will uptake from the groundwater in the soil. it'll move up through the plant body and evaporate through the leaves. And so basically, transpiration is just evaporation of water through the leaves. Over here, you see the word sublimation, and that's what happens when water molecules go straight from the solid form of water, which is ice, into the gas form of water, which is, again, water vapor. And this will happen in situations where it's cold and it's very, very dry, and you have, in general, low pressure. So we have low pressure the higher that we go into the atmosphere. And so instead of going into the liquid state, the ice melting, it goes straight from the ice into the gaseous phase. And so that's sublimation. But really, I mean, it's sort of the same idea where the water molecules can go up into the atmosphere. Just this time it's going from a solid to a gaseous form instead of a liquid to a gaseous form. Okay, so the last thing I want to talk about is just sort of an interesting look at something that I really just wasn't, I mean, aware of. I guess maybe I was aware of it, but it really helps to look at it on this paper. And that's the average residence time for water molecules. And what does that mean? Well, it's basically how long a water molecule will stay in a certain area. So I said that, maybe I said in the beginning that humans are involved in the water cycle. Let's just talk about that. So we have to drink water, and biospheric just means any living organism has to ingest water, either in the food that we eat or directly drinking. And the water molecules that we use in our body, we know that we expel them, excrete them in one way. But other water molecules that might get taken up into cellular processes, at most, they might stick around in our system for a week. If they're in the atmosphere, they might stick around for 1.5 weeks. If they're in rivers, that might be 2 weeks. If it's in moist soil, that could be anywhere from 2 weeks to a year, depending on a lot of different environmental factors. If you're in a wet, damp, muggy swamp, that water molecule could stay around for 1 to maybe 10 years, a decade. If it's in a lake or a reservoir, which is just a big body of water that's probably man-made, it can stay up to 10 years. But look at this. If it's in the ocean or a sea, it can stay as a water molecule in oceans for 4,000 years. Now, that's pretty interesting to think about, because if it's in the ocean or a sea, it's going to be salt water, which is unusable anyway. And so in order for it to become usable, to evaporate and become rainwater, that might not happen for 4,000 years. But you also have to remember that 97% of all the water on Earth is found here. But if it's in the groundwater, it could either last 2 weeks or up to 10,000 years. So even being in the ocean is more accessible, more timeline accessible than it is being in the groundwater. And the last one I want to talk about is those in the glaciers and the permafrost can be up to 10,000 years, right? If it's in the permafrost. Unfortunately, we know that the glaciers and the permafrost aren't sticking around at the rate that we would like them to. And so it'd be interesting to, well, interesting in sort of a dark way to find out what happens as the water that's trapped in these glaciers and permafrost is released. And so that's going to be a story for another day. But to not leave you on a sad note, this is just an interesting thing to talk about when we think about how we get the water that we use, and how we can think of, perhaps in the future, accessing water that was previously inaccessible, maybe from oceans or from wastewater that we produce. Anyway, so that's where I'm going to stop. That was the water cycle. If you have any questions, feel free to ask me, and I'll see you next time.